Okay, in this lesson, we're going to talk about the proofing technique of mathematical induction. Suppose that a sequence of blocks is numbered 1, 2, 3, 4 on forever. So it's sitting on an infinite table. So I got infinite number of blocks sitting on an infinite table. And some of the blocks are marked with an X. So like block 1's marked with an X, block 2's marked with an X, block 3's marked with an X, and so forth. Suppose that the first block is marked. So in other words, block 1 you know is marked. And furthermore, you know that for all n blocks, if block n is marked, then block n plus 1 is marked. So for example, block 3 is marked, and so is block 4, because if n is 3, n plus 1 is 4. If both of those conditions are true, then we claim that 1 and 2 imply that every box is marked. Every block is marked. Because you're saying, okay, the first block is marked, and then you're saying for any arbitrary number n, or for all n, if block n is marked, then so is n plus 1, the one right after it. So by assumption 1, we know block 1 is marked. By assumption 2, we know block 2 is marked. Because if n is 1 and it's marked, then n plus 1, which is 2, also has to be marked. Now, if I know 2 is marked, then by assumption 2, I know 3 is marked. And if 3 is marked, then by assumption 2, I know 4 is marked. And it just goes on forever. This process, or this principle of mathematical induction, is this process. Suppose that we have a propositional function Sn whose domain of disclosure is a set of positive integers. Suppose that you know S1 is true. And for all n greater than or equal to 1, you know that if Sn is true, then Sn plus 1 is true. Then that means that Sn is true for every positive integer n. Okay. So this is the principle of mathematical induction. Let's do an example. We'll start with the classic example of summing the first n numbers from 1 to whatever n is. Okay. So the notation for this is I equals 1 to n of I, which equals 1 plus 2 plus 3 plus 4 plus 5 plus blah, blah, blah up to n. The claim is if I take 1 plus 2, which is 3, and 3 plus 3, which is 6, and 6 plus 4 is 10, 10 plus 5 is 15, and so far, all the way up to n, the answer will be the same thing as just taking the formula n, take n, put it there, multiply it by the next number up, and divide by 2. So for example, if you go 1 plus 2 plus 3 plus 4 plus 5, okay, turns out to be 15, right? 3, 6, 10, 15. If I take 5 and put it there, I've got 5 times 6 divided by 2. 6 divided by 2 is 3. 5 times 3 is 15. That's an example of this formula working for n equal 5. Induction enables us to show that it'll work for any n greater than or equal to 1. So to do that, we have those two steps 1 and 2 that I looked at earlier. Step 1 is called the basis step. Step 2 is called the inductive step. In this example, the basis step will be n equal 1. I equals 1 to 1 of I. It's just going to be 1. So we'll take n equal 1, plug it in this formula. So put a 1, wherever there's an n, I put a 1. So I get 1 times 1 plus 1 over 2. Well, 1 plus 1 is 2. 2 times 1 is 2. So you have 2 over 2, which equals 1. So I now know that this formula works for the case of n equal 1. I could check it for n equal 2, 3, or 4 if I wanted to, but 1 is enough. Now let's look at the inductive step. For the inductive step, we have to assume that it works for some arbitrary k greater than or equal to 1. Okay. So we assume it works for I equals 1 to k of k. So what does I equal 1 to k of k mean of I? It means 1 plus 2 plus 3 plus 4 up to k. And we're assuming that if I add all those numbers laid out up to k, it'll end up equaling k times k plus 1 over 2. We want to now show that if I change that k to k plus 1 and do the same formulation, it'll end up as k plus 1 times k plus 2 over 2. Because think about it, if n is k plus 1, then by the original formula, you'd have a k plus 1 here, and then you'd have a k plus 1 plus 1. Well, k plus 1 plus 1 is k plus 2. To prove this, we'll take this summation I equals 1 to k plus 1, and we'll say, well, that's the same thing as saying the summation of I equals 1 to k of I plus k plus 1. So if you think about it, the summation from 1 to 5 is the same thing as the summation of 1 to 4, and then you just add 5 after it. That's what we're doing here. Why are we doing that? Because by assumption, we know the formula for the summation of I equals 1 to k of I. Okay? So now I can say the summation of I equals 1 to k plus 1 of I is equal to the formula for this guy, which is k plus 1 over 2, plus that k plus 1. Now to add the two things together, I need a common denominator. So I'm just going to take k plus 1 and say 2 of those over 2. And then if I add the denominator, since they're both of the same denominator, I can write it once and I just add the numerators. And then I note k plus 1 is common to both terms. I can factor it out. If I factor k plus 1 out, it would be k plus 1 times k plus 2, which is exactly what I get, what I want. Therefore, I've shown that this formula works now for k plus 1. Okay. And that shows that the below formula is true for all positive integers because I showed that it worked for 1. Okay. Then I showed that if I pick any arbitrary k and assume it works for that k, it'll work for the next one up. And then I go back to 1. It works for 1. Therefore, I know it's going to work for the next one up, which is 2. Then I know it's going to work for the next one up, which is 3. So no matter what n I plug in there, I'll know it'll work for the next n plus 1. So it just goes on forever. It works for 1, therefore it has to work for 2. It works for n equal 3, or rather n equal 2, therefore it has to work for n equal 3. Works for n equal 3, therefore it has to work for n equal 2. Okay. Next thing we're going to look at involves n factorial. So n factorial is a function. You plug in a value n. If n is equal to 0, then you get a 1 as an answer. If anything is greater than equal to 0, greater than equal to 1, the answer is you take whatever n you put in there, you multiply it by the next number below it, then you multiply by the next number below that, and you go all the way down to 1. Okay. If n is 0, we define 0 factorial as 1. That's what this is doing. And then if it's greater or equal to 1, you use this formula. There is no negative factorial. So the domain of n factorial is 0 to infinity. So here's an example. 0 factorial equals 1. So does 1 factorial, because 1 factorial would just be 1. 3 factorial means 3 is greater than or equal to 1, so it's going to be 3 times 3 minus 1, which is 2, all the way down to 1. So 3 factorial, 6. 6 factorial is 6 times 6 minus 1, which is 5, times 6 minus 2, which is 4, times 6 minus 3, which is 3, times 6 minus 4, which is 2, times 6 minus 5, which is 1. And then you multiply those numbers, you get 720. Now that we've defined what n factorial is, we're going to use mathematical induction to show that n factorial is greater than or equal to 2 to the n minus 1 for all n greater than or equal to 1. Okay. Our basis step will be to set n equal 1. Since my statement was for all n greater than or equal to 1, my basis step will start at 1. N equal 1. 1 factorial, as we just showed, is equal to 1. That's going to be greater than or equal to 2 to the 1 minus 1. or 2 to the 0, which is 1. So 1 is greater than equal to 1. So the basis step, n equal 1, this relationship is true. The inductive step says, okay, we're going to assume the equality is true for a value k greater than or equal to 1. We assume k factorial is greater than or equal to 2 to the k minus 1. And we want to show that k plus 1 factorial is greater than or equal to 2 to the k plus 1 minus 1. And you note k plus 1 minus 1 is just k. So we want to show that k plus 1 factorial is greater than or equal to 2 to the k. Okay. So we'll start with k plus 1 factorial. K plus 1 factorial can be rewritten as k plus 1 times k factorial. Again, because if you look back to the definition of factorial, sorry, I went too far. N factorial is n times n minus 1 down to 2. Well, I could also say n minus 1 times n minus 2 down to 1 is n minus 1 factorial. So n factorial could just be written as n times n minus 1 factorial. And that's what we're going to use here. So that's just using that fact. Now, k plus 1 times k factorial is clearly going to be greater than equal to k plus 1 times 2 to the k minus 1. Because we assume that k factorial is greater than 2 to the k minus 1. So therefore, k plus 1 has got to be greater than 2 to the k minus 1. So we're making that jump. Okay. That term has got to be greater than equal to 2 to 2, because if k is 1, you get 2. If k is anything bigger, you're getting something bigger than 2. So this term has to be greater than this. Okay. But 2 times 2 to the k minus 1 is the same thing as 2 to the k. Therefore, k plus 1 factorial is going to be greater than equal to 2 to the k. And that proves it. Right? So now we know that when n is 1, or 1 factorial is greater than equal to 2 to the 1 minus 1 or 1. Okay, so we know it's true for n equal 1. This is saying if I know it's true for any given n or k value, it's greater than the next one. It's true for the next one up. So since I know it's true for n equal 1, I know this equal greater than thing is going to be true for n equal 2, because if it's true to n equal 1, you've proven that it's true for the next one up, which is n equal 2. If it's true for n equal 2, you now know it's true for n equal 3. And if it's true for n equal 3, you now know it's true for n equal 4, and it goes on forever. So that's using mathematical induction to prove this equality. Here's another one. This is a thing called a geometric sum. So what does say? You have a number a and r. Okay. And r is not equal to 1. Okay. So you start with a. The next number is a times r. So ar is the previous number a times r. The next number is ar squared. Ar squared is ar times r. So ar squared is the previous number ar times an r. And all the numbers are like that. Ar cubed would be the next number. Ar cubed is ar squared times r. And this goes on up to n. And the claim is that sum equals this: a times r to the n plus 1 minus 1 over r minus 1. This sum is called the geometric sum. And a geometric sum, when a is not 0 and r is not 0, the ratio of adjacent terms, meaning the next one up divided by the previous one, will always be r. That's because each term is a previous number times r. Okay. We're going to prove by mathematical induction, so we have to have a basis step. The basis step here will be n equals 0, which means a is going to equal to a times r to the 0 plus 1 minus 1. Why is it a? Because when n is 0, it's just the first term, a. So a to the r 0 plus 1 minus 1, which would be A, 0 plus 1 is 1, so R to the 1 is R. So you got A times R minus 1 divided by R minus 1. The R minus 1s cancel. You get an A. So it works for n equals 0. A should equal A. Now we're going to do the inductive step. The inductive step says assume the formula works for n equal k, meaning A1 plus AR to the, A times AR to the 1 times AR plus AR, and start over again. A plus AR to the 1 plus AR squared plus dot 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 plus AR to the k equals A R to the k plus 1 minus 1 over R minus 1. We now want to show that the formula will work if n is up to 1, n is up to k plus 1. Okay. There it is. A plus AR1 plus AR2, da, 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 plus one more term, AR to the K plus 1. So notice everything up to the very last term is this, right? A up to ARK. You have A plus AR1 plus AR2 up to plus ARK is in this formula. So what that means is I can rewrite this and take the first A plus up to ARK can be substituted with the formula right there, plus this one other term. Then you just do algebra. In order to add these two terms, I got to have a common denominator of R minus 1, which means this right-hand term, ARK plus 1, I've multiplied R minus 1 over R minus 1, and then I wrote it over one term because it's a common denominator. Notice now I have an A in common to both of them, so I'm going to factor that A out. Factor that A out, then what's left inside is R to the K plus 1 minus 1 plus R to the K plus 1 times R minus 1. Now what I'm going to do is multiply R to the K plus 1 times R minus 1. So in other words, I'm going to distribute R to the K plus 1 times R minus R to the K plus 1 times 1. Okay. So that turns into this right here, R to the K plus 2, because if I take R to the K plus 1 and I multiply by R to the 1, you add the exponents, K plus 1, which is K plus 2. And then I'm just multiplying R to the K plus 1 minus 1. And notice that at the beginning of this expression, I have RK plus 1. At the beginning, I have minus RK plus 1. So they cancel out. They're gone. And all I have left with is minus 1 plus R to the K plus 2. And since order of addition doesn't matter, I reverse the order, and I get R to the K plus 2 minus 1. And that's the A still on the outside, divided by R minus 1. And that's what I should get, because the formula says whatever n is, it's A to the R n plus 1 minus 1 over R minus 1. And n was K plus 2. So there you go. It worked. I've now shown that that geometric sum formula is true for any n greater than or greater than equal to 1, I guess. So I just proved that formula to be true. N greater than equal to 0. And that's what mathematical induction, because you can do that, you're using the logic of mathematical induction to show that the formula works for any n. We'll do the same thing again with this example. Use induction to show that 5 to the n minus 1 is divisible by 4 for all n greater than equal to 1. Since it says n greater than equal to 1, I'll set my base case n equal 1 and plug into this formula. So n equals 1, I got 5 to the n minus 1 is 5 to the 1 minus 1. 5 to the 1 is 5. 5 minus 4 is 4. 4 is clearly going to be divisible by 4. Any number is divisible by itself. All right, so now we'll do the inductive case. We assume that 4 divides 5 to the k minus 1. We are assuming that. We need to show that 4 will therefore then divide 5 to the k plus 1 minus 1. So we're going to use the fact that if P and Q are each divisible by J, then P plus Q is also divisible by J. And in our case, J happens to be 4. This is something I can show in a later section that when we look at the number theory a little bit, we'll prove this is in fact true. Okay. So I'm going to we're now going to look at 5 to the k plus 1. Now notice 5 to the k plus 1 minus 1 could be written this way, 5 times 5 to the k. Because think about it, if I have 5 times 5 to the k, remember the rules of exponents, if the base is the same, you write the base and you add the exponents. So the base is 5, I write that, and then they add the exponents k plus 1. So all I'm doing here is rewriting this way. But now notice I have 5 units of 5 to the k minus 1. Now what I'm going to do is take that 5 units of 5 to the k and break it into two pieces. 4 units times 5 to the k plus 1 unit times 5 to the k. And then the minus 1 just carries down. Now, think of my p as 4 times 5 to the k and my q as 5 to the k minus 1. Okay. 4 times 5 to the k, clearly divisible by 4. Any number that's 4 times something is divisible by 4. So this is divisible by 4. 5 to the k minus 1 is divisible by 4 by our assumption. So think of p as 4 times 5 to the k. Q is 5 to the k minus 1. They're both divisible by 4. Therefore, this sum is divisible by 4. But this sum is equal to that, which is equal to 5 to the k plus 1 minus 1. Therefore, we've proved it works now for 5 to the k plus 1 minus 1. Good. So again, the base case was n equals 1. We showed that 5 to the 1 minus 1 was 4, which is divisible by 4. Now we showed that if we assume it's divisible by any arbitrary k, it's divisible, if 5 to the k minus 1 is, we showed if we assume 5 to the k minus 1 is divisible by 4, we proved that 5 to the k plus 1 minus 1 is divisible by 4. So if we set k to 1, we know that 5 to the 1 minus 1 is divisible by 4. That means now set k to, so set k to 1, I guess now set k to 2. Well, sorry. Yeah, if k is 1, then k squared, 5 squared minus 1, which happens to be 25, minus 1 is 24, is divisible by 4. So that means for any k I pick, if I know 5 to the k minus 1 is divisible by 4, then so is the next one. So I know 1 is divisible by 4. Then when k is 2, I know it's divisible by 4. And if it works for 2, I know that the next one up, which would be 3, 5 to the 3 minus 1 will be divisible by 4, and it just goes on forever. Now, you might remember from our set theory lecture, we talked about if a set had a cardinality of n, meaning a set contained n elements, then we defined what was called the power set. The power set was the set of all subsets of X. And remember that the empty set and the whole set itself was included in that set of subsets. And we stated that if the cardinality of the set is n, then the cardinality of its power set, which we denoted px, is 2 to the nth power. So if a set had 3 elements, it had 2 to the 3 or 8 subsets. We didn't really prove it then. We didn't have the machinery to do it, but we can use mathematical induction now to prove this is true. Okay, and in fact, the statement is if X is a set with cardinality of X equal n, then the power set's cardinality is 2 to the n. And this is true for all n greater than or equal to 0. So since I said n is greater than or equal to 0, my basis step is n equals 0. Okay. If n equals 0, that means X is the empty set. So the only subset of the empty set is, in fact, the empty set itself. Thus, the power set of X in this case is 1, which is also happens to be equal to 2 to the 0, right? Because any number to the 0 is 1. So my basis step works. It's kind of interesting how we're going to do the inductive step, but here's how we can do it. We're going to assume that the cardinality of X is K, just some number. And thus, the cardinality of its power set is 2 to the K. So we're going to assume that holds for some k. Now we're going to let X be a set with k plus 1 elements. Okay. And we're going to choose little x to be an element of X. And we claim that exactly half of the subsets of X contain little x, and exactly half of the subsets of X do not contain little x. If you look at a simple example over here on the right, you'll see X is a set ABC. If I write out all its subsets, here they are: empty set A, AB, AC, B, ABC, C, and BC. Okay, there's 8 of them. Right? These are all the subsets of ABC. Notice that exactly half of these subsets contain the letter A, and half don't. And that's true for anything. Half of them contain the letter B, and half don't. They didn't list that here. You just look at the A case. So all the A, there's 4 of them with A, 4 of them that don't have A. And if I was to use B, there'd be 4 with B and 4 without B, so forth. Okay. So that's what he's talking about here. Therefore, exactly half of the subsets of X contain X, and exactly half of the subsets of X do not contain X. So what we're going to do is we're going to let Y be the set obtained from X by removing X. So Y has K elements. Okay. By the inductive assumption, the cardinality of PY is 2 to the K. Okay. But the subsets of Y are precisely the subsets of X, right? Or I should say, yeah. Are precisely the subsets of X that do not contain Y. So in other words, the subsets of Y are precisely the subsets of X that do not contain X. Okay. So subsets of the set capital X do not contain the element little x. In this argument, I can say the cardinality of P of Y is the cardinality of P of X divided by 2, because we said that, the number Y will have the number of subsets of Y will be half of the number of subsets of X. Okay. Therefore, the cardinality of Px is 2 times Py, just, solving for Px, multiply both sides by 2, which means 2 times the cardinality of Py, which is 2 to the K. So 2 times 2 to the K equals 2 to the K plus 1. Thus, the theorem holds for K plus 1, and the inductive step is complete. And by the principle of mathematical induction, the theorem holds for all n greater than or equal to n. So now you know for sure that any set that has n elements will have 2 to the n subsets. The last mathematical induction problem we'll look at is the example of something called a right tromino. So it's kind of like a domino, but there's 3 squares instead of 2. Hereafter, I'll just simply call it a tromino. A right tromino is an object that's made up of 3 squares, and one of them's on top of the other, so you get this line has a right angle. Okay. A tromino is a type of polyomino. Since polyominoes were introduced by Solomon W. Golomb back in 1954, they've been a favorite topic of recreational mathematics. A polyomino of order S consists of S squares joined at the edges. So a tromino is a polyomino of order 3. Which is really 2 ways they could have one. You could have the right one that I have pictured up here, and then you could have one that's just 3 squares in a row, in a line. We're only interested in the right one. But a tromino could either be the right tromino or one with 3 squares in a line. A domino, as you know, is just a block with 2 squares hooked together. And that's, with little dots in them, and everybody plays dominoes. This is just an extension of that to 3 blocks. In this example, we're going to show Goulomb's inductive proof that if we remove one square from an n by n board, where n is a power of 2, we can tile the remaining squares with right trominos. By tiling a figure by trominos, we mean covering up the remaining squares with right trominos without having any of the trominos overlap. We refer to a board with one square missing as a deficient board. So if you think about a checkers or chessboard, those are 8 rows by 8 columns. 8 is 2 to the 3. So if you were to cut out one square, you could cover the remaining squares with right trominos. All of the remaining squares without any of them overlapping or anything like that. Okay. We'll now use induction on K to prove that we can tile a 2 to the K by 2 to the K deficient board with trominos for all K greater than or equal to 1. Okay. Example here, I got to start with a basis step. I'm going to start with K equal 1. So if K equals 1, 2 to the K by 2 to the K means 2 to the 1 by 2 to the 1, which means 2 rows, 2 columns. So 4 squares on your board. If you take one square out, what you're left with is a tromino. So in other words, here is 2 rows, 2 columns. If I cut out this lower right square, then what's left is a tromino. So one tromino covers that. And it doesn't matter which square. If I take out the lower right or I take up the upper right, I still can cover what's remaining with a tromino. If I take out the upper left, I can cover what's remaining with a tromino. If I take out the lower left, I can cover what's remaining with a tromino. So it works for K equal 1. We can now go and do our inductive step. The inductive step says assume that we can tile a 2 to the K by 2 to the K deficient board. Okay. We show that we can tile a 2 to the K plus 1 by 2 to the K plus 1 deficient board. That's what we got to do. So if we assume we can do it for 2 to the K by 2 to the K, for example, say K was 3, if we assumed it worked for 8 by 8, we need to show that it'll work for 16 by 16. Because if K is 3, then 3 plus 1 is 4, 2 to the 4 is 16. So by the assumption that we're doing this, we're assuming that we can tile a 2 to the K deficient board, one that'll have 2 to the K rows, 2 to the K columns, just by removing one of the squares out. So I remove one square, all the rest of the squares can be covered with right trominos. That's what we're assuming. Okay. Since we're assuming that we can tile a 2 to the K by 2 to the K division board, we now have to show that we can tile a 2 to the K plus 1 by 2 to the K plus 1 deficient board. Okay. Okay. So now let's look at a 2 to the K plus 1 by 2 to the K plus 1 board. The number 2 to the K plus 1 can be written as 2 times 2 to the K. Okay. This means that the number of rows and columns of a 2 to the K plus 1 by 2 to the K plus 1 board is twice the number of rows of columns of a 2 to the K by 2 to the K. So that means, see, if this is 2 to the K plus 1 by 2 to the K rows and columns, I can divide it up into 4 sections, and each section is 2 to the K by 2 to the K. Okay. So notice if I take a right tromino and I lay it right in the middle of these 4 boards so that this upper square is covering one of the squares and this 2 to the K by 2 to the K in the upper right, then one squared is also covered by the 2 to the K by 2 to the K in the lower right, and then one square covers one of the squares in the 2 to the K by 2 to the K in the lower left. Okay. Covering one square in this upper right corner is essentially removing it, and then you know that the remaining squares in the upper right corner can be covered with trominos because of our assumption. Same thing with the one down here. By laying this on top of the upper left square of this guy, it's essentially taking it out of the picture, which means the rest of them can be covered by right trominos. Same thing with this one over here. This one up here, I actually take out a square and I can cover the rest of those. Hence the whole 2 to the k plus 2 to the 1 k, 2 to the k plus 1 by 2 to the k plus 1 board is covered by right triominoes except for the place where I took one out, which therefore shows that if it works for 2 to the k by 2 to the k, it will also work for 2 to the k plus 1 by 2 to the k plus 1, which means our statement now is true. For any board that's a number of rows and number of columns is the number is equal to 2 to a power. So like 2, 4, 8, 16, so forth. If I knock out one square of that board, all the remaining squares can be covered with trinomials. And we proved it using mathematical induction. Okay. So that is our lecture on the concept of mathematical induction.